Greetings, physicists, and welcome back to Chapter 16, where today we will be discussing heat transport. I guess you can't see that. I'll move the camera over. My apologies. Anyway, we're going to be talking a little bit about heat transport, or how it is that heat gets from one place or one system to another. And to begin, let's go back to our discussion of temperature being a measurement of the average kinetic energy of the particles in a system or a substance. This kinetic energy, or heat, of course, is in the form of the motion of the individual particles as they're moving around in the substance, whether it's vibrating if they are a solid, or moving around relative to each other if there is some kind of fluid. Now, if one substance comes into contact with another substance, and the particles of one substance vibrate against the particles of the other substance, they can transfer some of their heat, right? Their kinetic energy can be transferred by direct contact. We call that conduction, and that is our first method of heat transport. Our first method was this thing we called conduction, or direct contact. That is one method that heat can get from one place to another. Now, some kinds of materials conduct heat very well, and consequently they're called, you might have guessed it, conductors. Metals in particular are extremely good conductors of heat because their outermost electrons are easily shared in between atoms and they can transfer the heat easily. And so metals conduct both heat and electricity incredibly well. Some materials are poor conductors of heat and are generally called insulators. Air is a good example of an insulator, or maybe styrofoam, right? Because you can put hot coffee in a styrofoam cup and you can't feel the heat from it, right? It doesn't conduct the heat through it very easily. But that is not the only way that heat can go from one place to another. What do lava, water, and air all have in common? They have convection currents. We already know that when you heat up materials, they expand. When they expand, they become less dense. When they become less dense, they rise. When they rise all the way to the top, they can shed some of their heat into another medium. At that point, the material then contracts and sinks down where the temperature is higher again, completing the convection current. And the classic example of a convection current is if you have water in a pot, right? You have heat from a fire or whatever heating the water here, and it expands, and as it expands, it rises. And when it gets to the top, it sheds some of that heat and it sinks again. And that makes a complete cycle, or a cyclical current. But there is also, so that one we call convection, right? C-O-N-V-E-C-T-I-O-N, convection, right? The currents. But there's a third method, and that, of course, is radiation. Namely, of course, electromagnetic radiation, or the thing that we call light. Now at this time I'd like you to refer to the electromagnetic spectrum diagram that I've included both on the lecture page and in the class files. So light, essentially, although not just visible light, we're also talking about everything from radio waves to X-rays, are also this electromagnetic radiation. And everything that has any real amount of heat gives off electromagnetic radiation, according to the Stefan-Boltzmann law, which of course means that something hotter is going to give off more light, and Wien's displacement law, meaning the peak color in an object, the higher the energy of the radiation itself is, the bluer in color the electromagnetic radiation is. The shorter the wavelength and the higher the frequency. And at this time I'd like you to refer to the diagrams of both the Stefan-Boltzmann law and Wien's displacement law in the diagrams, both on the lecture page and in the course notes. Now we, human beings, are brightest in the infrared portion of the electromagnetic spectrum. Your skin actually radiates infrared light, which you can't see with your eyes, but if you have those firefighter goggles, you can see body heat signatures even through smoke, and that's why it's such a handy technology for them. The cosmic microwave background radiation, which is one of the biggest pieces of evidence that we have for the Big Bang, because there is some energy, some heat essentially, some electromagnetic radiation everywhere in the universe that is left over from the Big Bang. It's very, very cold. It's about 3 Kelvin, and so its peak is in the microwave portion of the electromagnetic spectrum, hence cosmic microwave background radiation. In any case, electromagnetic radiation all moves at the speed of light. Some have higher frequencies with shorter wavelengths, and some have lower frequencies with longer wavelengths. But which electromagnetic radiation has more energy? The one with the longer wavelength or the one with the higher frequency? Well, that one, it may be tempting to think that the wavelength is really the thing, but if you just imagine which of these two photons is going to have more energy, the one that oscillates slowly or the one that oscillates quickly? Right? Obviously the one that oscillates quickly has more energy, and so the photon, the kind of radiation that has a higher frequency and a shorter wavelength, has more energy in it. And this is why some stars are blue and some stars are red. Smaller, cooler stars are redder in color, and the bigger, brighter, hotter stars are bluer in color. Does anybody know what the brightest color from the sun is? Believe it or not, if you look outside, you'll see the evidence. It's actually 550 nanometers or green. And that's why all the plant life on Earth has evolved green at 550 nanometers to take advantage of the sun's energy for photosynthesis. Now, I've also included a picture of, or a diagram, excuse me, of the Hertzsprung-Russell diagram. And that's a map of the population of stars that we've been able to map out. Now, you'll see down at the lower right, or towards the right just in general, the surface temperature is lower, right? And so the stars are redder. And on the left, the stars are bluer because they're hotter. In the middle, the stars turn white. Why are there no green stars? Well, the answer lies in the visible, in our interpretation, excuse me, the visible portion of the electromagnetic spectrum, and of course our understanding of the Stefan-Boltzmann law. According to the Stefan-Boltzmann law, so if we have down here like the wavelength, and here you have the brightness or the luminosity, every black body source is going to have a curve like this with a peak somewhere. And if you're on a star that has a peak somewhere in the green, you're going to have a certain amount of blue light and a certain amount of red light. And if you have enough red, green, and blue all add up together sort of evenly, the color that you emit, the color that you get from combining these three primary colors is white. And that's why there are no green stars, but in the middle of the spectrum, right, in the middle of the main sequence in particular, there are a lot of white stars, but no green ones. In any case, this radiant energy can be emitted, but it can also be absorbed, right? It's light. That's why if you're wearing lots of black, then your clothes will absorb a lot of the sun's radiant energy. But since it's light, it can also be reflected. Like if you wear white, or if you have, reflective surface on, you have one of those space blankets, or you have a bunch of reflective strips, then the reflective surface can reflect it. Like if you have one of those shift pods or a yurt with a reflective coating on the outside, that can reflect the heat outside of your tent and keep it cooler. At night, an object can radiate the energy out into space, so it can get cold very fast. Now, space doesn't generally give much heat energy through light, does it? Space is cold and dark. Newton had an expression for how quickly the heat goes in between two objects or substances. If two objects have a similar temperature, then they come to an equilibrium relatively soon. But there isn't much heat being transported between them. If two objects in contact have a huge temperature disparity, then the cold one will absorb more heat from the hot object per unit time. And the hot object will, of course, conduct more heat into the cold object, the greater the temperature disparity. And this is why wind chill is a factor. A wind chill factor of 20 degrees means that the objects that are getting whipped by this fast wind will lose heat as if they were in contact with a 20-degree colder environment, because they're coming into contact with more air particles from the wind pushing past them. And we already talked about climate change, so there's really no need to go over that again. But I want to talk to you a little bit about one of our more handy inventions, one of these things that you've probably used before. You've probably been using since grade school and not even realized it. But there's this thing called a thermos. God, I'm terrible at drawing. Okay, so we've got an inner thing, right? And then there's like an outer layer. And then you've got like, some kind of lid, and then, there's like a cup that goes on top of it, usually something like that, right? So why is it that a thermos is able to keep things hot, or alternatively cold if you put something cold in it, for a long time? Well, is there any heat going in between the stuff that's on the inside here and the environment? Well, a little, but not a lot. The thermos actually has two walls that are separated in here by a vacuum. And since there's not a lot of material in here, there can't be a lot of heat transferred by conduction. Right? The vacuum cannot conduct heat as there is no matter in it. And as there's no fluid in the vacuum, there can be no convection currents causing heat to go from in between, right? There's no material inside here, it's a vacuum. Now, if you've ever looked inside a thermos, you've probably been able to see that the inside walls are shiny, right? So that if any heat or, any radiation, right, any light gets in or out of there, it's not going to be able to transfer the energy out, right? So radiation is blocked by this shiny inner coating. And a lot of thermoses are even shiny on the outside too, in order to keep the heat loss to radiation at a minimum. And that's why a thermos is able to keep your soup hot and your drinks cold for a very long time, because they engage very minimally only in these three things. The three main methods of heat transport. In any case, I hope you've enjoyed this video, and I'll see you again soon for Chapter 17.